Imagine 1,000 individual data points hitting you all at once. The human brain cannot process large bursts of unorganized information at scale. We are wired to recognize small patterns, but throw a massive, chaotic swarm of numbers at us, and our comprehension immediately shuts down. To solve this, we force physical order onto the chaos. This is the simplest level of data handling, the tally. We take abstract units and lock them into uniform rows. Counting individual lines one by one is slow and prone to error. By striking a diagonal line across every 4 marks, we create discrete blocks of 5. This leverages our eye's natural ability to subitize, to instantly recognize small clusters without consciously counting them. But this system has a hard limit. Expand the volume of data from dozens to thousands, and those neat little blocks of 5 become just as blinding as the raw numbers we started with. The methods we use to organize data are engineered tools. We invent these systems specifically to bypass the biological limits of our own perception. When the volume of data outgrows the tally, we compress it. By establishing a key or scale, a single geometric icon absorbs the value of hundreds or even thousands of individual units. This creates a pictograph. With it, we gain a new cognitive ability. We can look at entirely disproportionate datasets side by side and immediately grasp the differences in volume with a single glance. What happens when a specific data point doesn't divide perfectly into that scale? If an icon represents exactly 1,000, how do you map an uneven number, like 342? Fracturing a picture mathematically destroys its visual meaning. You end up guessing a value based on a mangled shape, sacrificing exactness. To visualize massive scale through pictures, we compromise strict mathematical precision. The pictograph is highly effective for quick comparisons, but it remains an approximation. To solve the pictograph's flaw, we strip away the pictures entirely and rely on strict geometric rules. The bar graph provides massive visual scale while maintaining mathematical precision. This system works because the geometry is rigid. The gaps between columns are identical, and the width of every column is locked exactly the same. If widths vary, optical illusions distort the data. Locking the width forces the human brain to evaluate only one moving variable, the length. How we orient lengths is dictated by the real world. The physical layout of a graph mirrors the physical reality of the data it represents. When measuring the heights of mountains, the data climbs upward from a flat ground zero. Therefore, we use vertical columns, growing upward from a baseline to reflect how these objects exist in reality. Conversely, mapping the lengths of the world's longest rivers tracks sweeping distances across the ground. The graph rotates, using horizontal bars that stretch left to right, mirroring paths drawn across a map. In data presentation, form follows meaning. The rigid structure of the bar graph allows us to visually compare massive datasets while preserving the precise mathematical value of every single entry. Often, designers try to make numbers more engaging by replacing boring rectangles with detailed illustrations. This is a chart showing 2 mountains as 2-dimensional triangles. To show that the second mountain is twice as tall as the first, an illustrator drags the peak upward, doubling its vertical height. Because it's a 2-dimensional object, dragging it taller automatically forces its horizontal base to expand proportionally. Expanding both the height and the width means the overall area of the shape is squared. The height doubled, but the sheer volume of the illustration tricks the brain into perceiving a 4-fold increase. Understanding these geometric rules acts as a critical defensive skill against misinformation. When math is manipulated for aesthetics, human perception bends with it. Data handling functions as a translation tool. By enforcing strict geometric rules, we gain the ability to detect where data is being visually distorted for the sake of a more dramatic picture.